Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. I hope the voice is coming. All right, so this session is about sketching the feasible region. I will keep it quick and short. Sketching the feasible region means that we have some time domain specifications, which are peak time, settling time, percentage overshoot, and omega n. Using this, we can define a region of the S plane, which will help us to define a region which will satisfy all these conditions. I'll tell you in a while what does it mean. Let me just. All right. So yeah, so we have these specifications. You can see settling time, peak time, percentage overshoot, rise time, and omega n. As such, we don't have anything for rise time, so we just ignore it. We just keep the four: TS, GP, PO, and omega n. These specifications can be used to define boundaries, such as, like you can see, uh, if you remember, the TS will give us vertical lines like this. So you can see that. Let me use my pointer. So one of this line is basically showing one settling time which is constant throughout this line. So if the pole moves on this line, the TS will remain same. Similarly, another vertical line will have another constant TS. If you move on these lines will have a constant yeah, TS. Similarly, for TP, as you remember, we'll get the horizontal line like this. So you can see that this is horizontal line here and this one. Please make sure that this omega 1 and omega 2 are actually the complete imaginary part. I'll tell you in a while, or maybe just let me write it down here. The pole is actually S equal, uh, let's say alpha as it is in this one, plus alpha plus minus j omega, which is in our case minus zeta omega n, which is different from omega, plus minus j omega n under root 1 minus zeta square. So this is omega and this is omega n. All right. So you can see that this omega 1 is basically one of the peak time representative, omega 2 is another. So all along this line, we'll have constant peak times. Then we have percentage overshoot, which can suggest angular lines, or we can see like this. So you can see that percentage overshoot represents a particular zeta, and then that represent a particular theta, as you can see in these lines. This one and this one are so on one of the red lines, the percentage overshoot will remain the same because the angle is same. Because the angle is same, the zeta is same. The zeta is same is percentage overshoot is same. Similarly, on the blue line, the angle is same, the zeta is same, and the zeta is same means percentage overshoot for that particular angle is same. Similarly, omega n can suggest circular lines. So it's like this one. I hope it's a bit clear now. So what can we do with this? So uh, this is the S plane. All right. So for a TS, we can have a vertical line. Let's just keep one at the moment. For TP, let me change the color. Purple. I like purple. TP will have a horizontal line, and of course, as we discussed yesterday, also there will be conjugate line, but I'm not drawing the one. Okay, let me draw it here, but I will not be drawing later on. Okay. Then we have for percentage overshoot. Let me change the color again. Okay, hello. We'll have a line something like this. For example, I should have drawn dotted line. Okay, and for omega n, I'm just drawing one at the moment. Green. For omega n, we will have, let's say, a circular line something like this. This is not the right line. It would be somewhere around like this. My drawing is not too good, but I hope that you guys get it. So, for example, the TS has to be greater. Greater means this way. So let's say TP is, let's say, smaller. Smaller means up. Percentage overshoot is suppose less than, so it has to be this one. And omega n has to be greater, for example. So it will be this one. So the region which is allowed comes out to be, let me change the color, black. This seems to be the feasible region. It is under this one, above this one, left, right of this one, and above this angular line. So this is the feasible region. Let's take an example. A control system is designed such that the step response settles between 5 and 10 seconds and has an overshoot not violating 10 to 20% between pi by 4 and pi by 2 seconds. The radian frequency can be between 1 and 3 radian per second. So first of all, we have to find what is given. As you can see that the step response settles. So this gives you an idea between 5 and 10 seconds. So this means this is somewhat about settling time. Okay. Overshoot is, as it is also hinting by the percentage, the overshoot is between 10 and 20%. And when does the overshoot occur? At the peak time. So this is the peak time. Okay. And the radian frequency omega n is 1 and 3 radian per second, as I'm going to show you now. So you can see in the question, settles between 5 and 10 seconds. So 5 and 10 seconds, which means that we have to use TS as a formula. And for this one, what is the formula? Formula is 4 upon zeta omega n. So from 4 upon zeta omega n using 5 and then using 10, we have to find zeta omega n. Okay, like this. So from this one, we can say the zeta omega n is 4 upon 5 or 0.8. Okay, and from this one, zeta omega n is 4 upon 10 or equal to 0.4. This means if I'm going to draw it on the S plane, there will be one line at minus 0.4 and one line is minus 0.8. So it would be something, I'm changing the direction based on my own desire. Like this, and another line at 0.8 like this. So it has to be in between these two. I could have drawn straight line actually. All right. It has to be between 0.4 and 0.8. I hope that this is making sense. Then we move to percentage overshoot, as we have highlighted, overshoot not violating 10 to 20%. So from percentage overshoot, we can get directly the zeta, and from that we can get the theta. So for 10%, I have done the calculation before. For 10%, the zeta is, you can use the formula. I will be giving you the formula in the exams. So the zeta is 0.59. And for 0.59, the theta angle would be, theta is cos inverse of 0.59, which is 54 degrees. This is degrees. All right. So, and similarly for 20%, the zeta is 0.45 and the theta is 63. This means I'm talking about this. Okay. So one is about 54 and one is about 63. So this is 54 and this is 63. So it has to be in between this. All right, is that clear? Oh, I'm asking nobody here. Okay, and then the pi by 4 and pi by 2. This is for the overshoot between pi by 4 and pi by 2 seconds. This means we are talking about the peak time. So peak time is between pi by 4 and pi by 2 seconds. The formula for peak time is pi upon omega n under root 1 minus zeta square, which is actually, I just told you at the beginning, is omega. Omega. Okay, this is the horizontal line value. All right. So when we keep pi upon omega n under root 1 minus zeta square equal to pi by 4, we can cancel out pi and pi. We get omega n under root 1 minus zeta square equal to 4. Okay. Right. If we can cancel this one. And similarly, for pi by 2, we get 2. So what do we get? We get on S plane, just to clarify, okay, we get one line at 2, one line at 4. This is this value. 4 and 2 are these values. And of course, we have the same on the bottom half of it, -2 and -4, but we can just focus on one side only. So far we have 2 vertical lines, 2 angular lines, and 2 horizontal lines. We have to like all put them together to find a feasible region. And where is that? Okay, I think keep insert new slide. So this one we have to look at the question. Question was the radian frequency between 1 and 3 radian per second. So we can go to, okay, here. So radian frequency is omega n between 1 and 3, I think, right? So it is already given. So this means we're talking about, let's say this is 1 and this is 3. So 1 should be something like this, and 3 should be something like this. It has to be in between. I didn't mention the previous one. It has to be in between here. All right. So now we have four types of boundaries. Let's go step by step, one by one again. We have 2 boundaries for vertical lines in this one. Okay. We have 2 boundaries for angular lines in this one here. We have 2 boundaries for horizontal lines, the red ones. Okay. And 2 boundaries for the circular line. This one. We have now superimposed them. We have to remember the values. So let's say this is 1, this is 2, this is 3, this is 4. And let's put it here 1, 2, 3, and 4. And since the values for the x-axis were small, let's put this as 1. Okay, this is 1. Or no, I don't think that's a good idea. Let's keep it same. So suppose this is 1 and this is 2. We don't need we need 3 as well. 3. Okay. So 0.4 would be somewhere. So the boundaries were 0.4 and 0.8, of course, negative. For x-axis, or not axis, let's z omega n. This is for, let's put it completely, zeta omega n between 0.8 and 0.4, omega n under root 1 minus zeta squared between, I think, 4 and 2 seconds, theta between 54 and 63, and omega n between 1 and, is my eraser, between 1 and 3. Okay, so 0.4 to 0.8 would be, let me be a bit flexible. So this is about 0.4 and this is, let's say, 0.8. So we'll have to have two lines. Let me do it using the lines here. So I'm using the line. So one line is like this, and another line is, let's say, like this. This has to move. Yes. Okay. So this is for zeta omega n. For this one, horizontal lines between 2 and 4. So between 2 and 4. All right. Okay. Then the angular length 54 and 63. I'm drawing approximately. So let's assume that this is 53 and this is, you will be given a proper graph paper, so don't worry. And this is 64, for example. Let me make it a bit flexible. All right, and this is the most difficult one. So 1 and 1 here. Since this is not to scale, it would be somewhere around, not bad. So this is for 1, and I think I can just copy this one, and 3. Approximately. I hope you would forgive me for my bad drawing. All right, so let's go there. I hope you can see that. So this one is minus 0.4, and this one is minus 0.8. This one is 2, and this one is 4. This angle is 53, and this angle is 53 and 64. And this radius, I'm assuming this is a circle, but because of the scaling, the x-axis is a bit longer, I think. So just assume that this is 1. So this is 1, and this is 3. Okay. Now remember that it has to be between this and this, and between this and this, between this and this, and between this and this. So which one is the feasible region? Anyone? There's no one. Teaching no one. So above this is this line, and left right of this, between this and this. So this is my feasible region. Coloring, I remember my coloring days in my school. Inside, go to the boundaries first, and yeah. So this region is the feasible region. All right, this is how we draw the feasible region, and this has to be superimposed on the root locus. If the root locus passes through it, we'll talk about that later. Okay, as I promised, I'll finish this within the 30-minute window. Any question? You can put in comments, like, subscribe, and share, and don't forget to click the notification button. All right, thank you.